All right, I'm just going to start a little bit farther back. So we did cover this in class today, but just so that I can go at like a nice, easy pace, I just wanted to point out that in this question where we're asking, are these salts going to be more soluble in acidic solution? The underlying question is your anion a base of meaningful strength? And so in the first question, nickel hydroxide, yes, OH minus is a base. Carbonate is a base, right? Fluoride is a base because its conjugate acid is a weak acid. And so fluoride is a weak base. So it does react with H plus. The place where an anion will not react with a base is if it's the conjugate base of a strong acid. So the only time that like this isn't going to be effective is if we have Cl minus, Br minus, I minus, NO3 minus, ClO3 minus, and ClO4 minus. So these are like, if that's your anion, then it's unlikely that acid is going to have an impact on the solubility of your salt. Okay, so just saying that, like I'm expanding, I guess, back from slide 22, where I said if it's a weak acid, it's more soluble, or the conjugate base of a weak acid. Really, like the blanket statement is if the anion is a base, then acid will increase the solubility of that salt. Okay, and then we jumped into complex ion formation, which again is kind of this like cherry on top of the sundae. And we started by looking at this silver chloride, which is insoluble, or I mean, and technically, and keep in mind now that we can sort of provide nuance to insoluble, like it's not either or, it has a KSP. There is some Ag plus and Cl minus in solution. It's just a very tiny amount. We can calculate the amount that would be x squared equals 1.6 times 10 to the negative 10th. And so X would be our molar solubility and the concentration of Ag plus and Cl minus. Okay, so we say it's insoluble because it has a very small KSP, but there are still Ag plus and Cl minus ions in solution. And then we go on to make this observation that, hey, when you put ammonia into solution with AgCl, all of a sudden, all of our AgCl dissolves. Okay, so add NH3, molar solubility increases significantly. And the question is, why is that happening? Well, we have the formation of a complex ion. Ag plus really likes to make a complex with ammonia. Did I pick the right number? Oh. No, I didn't. It's 2 in this case. It's 2. A diammonia complex. And this, the reason why this is so effective at dissolving the silver chloride is because this has a huge K value, and that's K of formation, so like our complex ion formation, and these are always big numbers, okay? In this case, it's 1.7 times 10 to the 7th. Okay, so we really favor the formation, and this is also in the aqueous phase. So as soon as we generate, even though it's a very tiny amount of Ag+, all of that Ag+ goes immediately to making this complex ion. So as soon as that goes, then this needs to dissolve more. But then if I make more, as long as I have more ammonia around, I'm going to keep making this complex because it is so favored at equilibrium. That's what makes this more soluble, is that we keep dissolving it a little bit. We make a little bit, but that little bit goes on to make this complex. And so we just keep dissolving more and more AgCl. We see that here. Here's our insoluble AgCl sitting at the bottom. Okay, it doesn't dissolve very much, right? Our image here shows just a couple, one Ag plus and fluoride ion in there. We put in ammonia, and all of a sudden we start making these complexes, which means we don't have like our Ks, we aren't meeting our requirement for the silver chloride KSP. In other words, I could put this in terms of in Q. So Q is equal to this like random time point. And what we're seeing is that Q at this point is less than KSP. So I need to keep dissolving more Ag plus and Cl minus to keep that same KSP value. And if we put in enough ammonia, then we're just going to form all of this complex ion and all of it dissolves. So there's all, it's all gone because all of it, we wound up making this complex. Okay. So we went over some rules of thumb, but again, at the end of the day, if you're wondering, is this a KF question? The answer to that is, or the answer is, did we give you a KF value? That's when we want you to think about a KF, is if we give you if we give you a complex ion KF value, then we want you to think about the formation of a complex ion. But I'm not expecting you to look at a salt and say, hey, are you gonna make a complex ion? No, we'll give you that information in the question. So that's like our red flag to say, like, hey, we want you to think about this. The general rules though are that metal salts, okay, increase, so metal salts being like where we have a cation, which I would consider as a Lewis acid, okay, because they are cations, so they are electron poor. So therefore they want to accept electrons. And these would be, like our Ag plus, our zinc 2 plus, our Fe3 plus. Okay, nickel 2 plus, any of these charged metals. Okay, and again, I'm not expecting you to know this or to predict it, but just so that you have some familiarity, if I put a salt with one of these cations in, and then I add a Lewis base, and we typically see those as our ammonia, right? It has an electron pair to give. Cn minus certainly has an extra electron pair to give. OH minus. These are the things that are going to come and like latch on and make these ions or complex ions with those metal salts. Again, I don't expect you to predict it. We will give you a KF with an associated complex. But you should know KF is always big. And so adding in this appropriate Lewis base is always going to increase the solubility. So the solubility of metal salts increase with the presence of that Lewis base. Okay. So this again is just Le Chatelier's principle. We have if we go back to what I was doing before, we're taking out the product. So the system responds by making more product, which means dissolving more AgCl. The KSP isn't changing, but I am dissolving more, which means that the solubility of silver chloride is increasing. Okay, and again, if you run into any questions in on Pearson that doesn't have a KF value, but you feel like you need one, well, that's not a rectangle. Those values are in table 17.1 and just go look them up. There are a couple quantitative questions that you might find in Pearson. I think I've made them practice problems on your homework. So do these if you're interested, but this is unlikely to show up on your exam. So these next two slides are examples of that. And I can post answer keys for those of you that are interested. I skipped over these two slides, and this was really just defining these, like what we already talked about. So we're going to look at zinc oxide again, but we're looking at all of these metal oxides and metal hydroxides where the metal cations will react with OH minus, usually to make a complex ion. So that increases the solubility. And then also the O2 minus or OH minus, that will react with H plus to make water. And so that increases the solubility. So we have amphoteric salts, which means that they will dissolve in both acidic and basic solutions. And that's because if with the addition of the base with our OH minus, we can consume some of the metal cation through the formation of a complex ion. And because the anion we are creating is very basic, it will react with H plus, and so we would consume some of that, which would mean we're increasing the solubility of our salt. So we're just looking at an example here where we have aluminum hydroxide. Okay, it's not very soluble. There it is sitting in solution. We add in some base, some OH minus. We make a complex ion. Okay, that is soluble. So that's like floating around. It's not making a salt because it's all negatively charged, right? So it's floating around in solution. Now you can see it's clear. There's nothing left in there. So there's the addition of base, which makes it more soluble. If we add in H plus, then we're going to consume some of our OH minus, right? And so that drives, we're going to make some of our, some water with H plus and OH minus, all right? So that explains why acid in this case would increase the solubility, okay? Then we came to this qualitative problem. This is a really common structure for questions on exams. Zinc oxide is amphoteric. In this case, we don't ask about adding OH minus, but we do talk about adding a suitable Lewis base. Okay, so for a saturated solution of zinc oxide, I noticed down here, so take note of all the information that you're given, which is probably, this isn't my like best setup. It's kind of hidden away down here. But the KSP of zinc oxide is 6 times 10 to the negative 16th. It's a really, really sparingly soluble. I think insoluble would be a good description. But of course, a very tiny amount has dissolved. Right? It has established some equilibrium. It's just a really small number. All right, and we know that this equals that 6 times 10 to the negative 16th. Okay, so I'm asking, as I add in these three things, okay, one at a time, not all together, and not in the same solution, what happens to the solubility and what happens to the KSP? When I add in zinc chloride, which is soluble, this is going to make the zinc concentration increase, the zinc 2 plus. Okay, so now this number gets really big, okay, which means that if I'm going to hold KSP constant, which I have to, I need to consume some O2 minus. And the only way to do that is to make some more zinc oxide, which means that we've reduced or decreased the molar solubility of our zinc oxide by adding in zinc chloride. This is the common ion effect. Okay, so this decreases the molar solubility and then doesn't change the KSP, because you will never answer that the KSP changes unless we change the temperature. All right, HNO3 is added. This makes H plus. Okay, and then we ask ourselves, is the anion going to react with H plus? O2 minus is an incredibly strong base, so yes, we make HO minus, or say OH minus, at 100%. Okay, so that means this concentration is now going down. We are consuming O2 minus. So we have to dissolve more of our zinc oxide to maintain our KSP. Okay, so we pull this out of solution, we need to shift right. Consume product, make more product. And then lastly, we have our ammonia that we're adding. And the key information here is that we give you the KF. Remember, so KF is provided. You know that zinc 2 plus likes to form this tetra ammonium complex, and it's got a big KF value. So when you put KF in, let me delete all my other chicken scratch up here. When I put my NH3 in, it reacts with the zinc 2 plus. So we're pulling zinc 2 plus out to make this complex, which drops this concentration. Remember, KSP has to stay constant. So we are going to have to increase the concentration of O2 minus, which means that we're dissolving more zinc oxide. Okay, so this increases the molar solubility, and then there's no change to the KSP. That was also the answer for this one. So increases the molar solubility and no change to the KSP. All right, so that's where we left off today. And I just got these last couple slides to talk about. And again, this is the fortunate thing about this is I know it's a lot of content, but we've already laid the groundwork for understanding all of this. Okay, so our precipitation and separation of ions. Okay, so we're really going to focus on precipitation here. Okay, so before we were saying like, okay, I've got this Erlenmeyer of water. Okay, and I'm going to add in some salt. Okay, my salt's going in, and I'm wondering how much will dissolve. Okay, so like how much dissolves? That was our question. But now we're going to take a solution. So like maybe of soluble salt. Okay, so maybe this is like NaCl. Okay, and I'm going to add it to, oh man, hold on. I can't think and draw an Erlenmeyer at the same time. We're going to add it to a solution with another soluble salt. So let's call this silver nitrate. Okay, and when we add it together, we are wondering, have we surpassed? We actually know that both of, so these two are soluble, but AgCl is sparingly soluble, or it's insoluble. Okay, and so we're wondering when we've combined these two mixtures, okay, and now it's really full because I've added these two volumes together. We're wondering, does AgCl form? Okay, so that's the image in your mind. We're wondering, have we put too much Ag plus and Cl minus in solution? Will it drop out? So this is actually just a Q question. Okay, in the Q comes, we calculate the Q from the concentrations of solutions added. And then we compare it to the KSP. So you're going to be provided a KSP, and then we have to see when we add two solutions together, are we surpassing the Q? If Q is greater than KSP, we've put too much of those ions into solution, and so we have to form some precipitate. If we find that Q is less than K, then the system is undersaturated or unsaturated, and we don't need to form a precipitate. We will likely avoid the situation because it's precipitous, where Q equals KSP, because that's like right at the top of the mountain. On one side, no precipitate forms, and then we fall over on the other side and precipitate forms. Like this is right at the balance where any additional ions means that a precipitate forms and it's technically saturated, but we will likely avoid a situation where our Q and K is so similar that you might have a Q equals K situation. Okay, so let's jump into this. Let's look at what an actual problem like this might look like. So does a precipitate form when 0.1 liters of 8 times 10 to the negative 3 molar lead nitrate is added to 0.4 liters of 5 times 10 to the negative 3 molar sodium sulfate? Okay, and so the first question is, what is the thing that might be precipitating? So even if you don't remember your salt solubility rules, what I see here is we're given a KSP that's pretty small for lead sulfate. Okay, so lead sulfate is the thing that we're wondering, is it going to drop out of solution? Is it precipitating? Okay, I have lead in here and I have sulfate in here. Okay, so I'm wondering, have I surpassed this KSP? So I need to calculate Q when I combine my 0.1 liter and 0.4 liters of solution. So Q, remember, has the same expression as KSP. So it's Pb2 plus times SO4 2 minus. I need those concentrations right when I've made my half liter of solution. Okay, so I'm not just going to pull these numbers because I need the concentrations when I've mixed them. So this is where what I call C1V1 equals C2V2 comes into play. Concentration 1 times volume 1 equals concentration 2 times volume 2. Okay, so let's do this for lead 2 plus first. So the initial concentration of lead was 8.0 times 10 to the negative 3 molar. And I had that in 0.10 liters. I'm wondering what my new concentration is after I dilute it to a total of 0.50 liters. Because I'm going to have a half liter when I combine these two. So my concentration of lead 2 plus in this new volume is 0.0016 molar. All right. And then sulfate, SO4 2 minus, okay, is going to be, and also notice, and I should point this out, I could just pull this molarity because there's one lead ion for every 1 unit of my lead nitrate. Okay, so this concentration is the concentration of lead 2 plus. Okay, that's also true for sulfate. But if we were concerned with the nitrate or the sodium, I would have needed to multiply by 2 because I have 2 units of the nitrate for every 1 unit of the salt. So just make sure you're paying attention to the formula of the salt. Just going through the same concentration calculation here. So my sulfate concentration is 0.004 molar. So these are the values that I'm going to plug in to my Q. So Q equals 0.0016 times 0.004. That is equal to 6.4 times 10 to the negative 6. Q is greater than KSP. 10 to the minus 7th is a smaller number than 10 to the minus 6. Therefore, I've put too many lead and sulfate ions into solution. I must make a precipitate. Okay,